So there's errors when we use the ideal gas law. And what we're going to do today is we're going to watch a few animations, and then we'll answer some questions on the animations, and then we'll get together in groups and we'll try to fill out the sheet that's on the last page of your handout. Okay, and then we'll call it a day. But in that handout, at the very bottom of it, is the real goal, I think, is just under what conditions does the ideal gas law give horrible, horrible predictions as to what the pressure, volume, or temperature will be. And that's kind of important to understand because, right, otherwise something like this could happen. If you expect the pressure or the temperature to be drastically different than what it actually is going to be, you're going to have all the little gauges set wrong and everything, no matter what the process is. So mistakes could happen. So that's why we're kind of talking about today. First, let's try to visualize molecular motion. And backing up a little bit, well, let's see here. Let's see if we can get this going. Oh, okay. Now, let's pick on somebody here. I already picked on Victoria. Kimberly, this is one gas molecule in a steel box, and you can kind of just see inside the steel box. So you can see the red dot, the red molecule there, sphere. So it must be like hydrogen, because it's just monatomic. But how does that differ from an ideal gas? What did we say an ideal gas was really composed of? Not molecules, but what? Do you remember? Does anybody remember? It was theoretical. It's pretty much ridiculous, because there's no way. It was all theoretical. Ideal gas was composed of, nobody remembers? We just spoke about it very briefly. Dots. Points in space, right? So can the point in space collide with itself? Alyssa? Yeah, well, not with itself. Can the point in space collide with another point in space? Well, they can overlap, but they can't really collide, right? And can they interact? Do they have any mass? A point in space, X, Y, Z. It's just a theoretical point in space, this location, right? There's no mass. They can't collide. They can't do anything what a real gas molecule could do, right? So if you take Alyssa, I'm going to push the little play button, and then they're going to allow the little gas molecule to move like a gas molecule they believe moves. How do you think it's going to move in that steel box? Yeah, how would you picture it? They're going to animate this. What is it going to do? So they move around. Would it be random? Yeah. And yeah, pretty much.
The path of one particle in a gas is very erratic. The particle will continuously change its course as a result of collisions with the walls of the container.
Right? So it's those collisions that create, with the walls of the container, that creates the what in the container? There's the P. The pressure, right? That's what all the pressure is, right? Just the collisions with the walls of the container. Let's see. Oh, this one. Now you have a whole bunch of molecules. Look at that. Why does it do that?
The paths of gas particles are very erratic. Particles continuously change direction and velocity as a result of collisions with other particles and with the walls of the container.
So did you catch that, Jerixa? Are they all traveling at the same speed? What did they say? Right? If you collide with the wall of the container, you're probably end up slowing down. You collide with another molecule. That other molecule could probably start speeding up and you'd slow down. The other one would slow down. So, I mean, they're going to be traveling at varying speeds. So there's some average speed, and that's really what temperature is all about. It's just the average energy of motion of that gas. Okay. So if we heated that up, what would happen to the motion, would you say, Jesus? Just stick a little flame under that steel box, heat it up, everything just starts moving faster. Colliding harder, the pressure would go up. None of that can happen with an ideal gas, because an ideal gas is just theoretical. What again? What's an ideal gas? Not molecules. Dots. Theoretical points in space. They can't do jack. Ooh, a point in space can move around, fine, but it can't collide. It can't. I guess you could make a dot and point in space move faster, but you can't make it collide. Okay, can't make it interact. Okay, so the kinetic molecular theory of gases. So all of these are differences between an actual molecule and an ideal gas. Gases are composed of molecules whose size is negligible compared to the distance between them. So I guess, maybe, Monica, they're trying to say a gas is mostly empty what? If you have a container, it contains a gas. The distance between them is huge. A gas must be mostly empty. Anybody see what I'm driving at? Empty space, right? A gas, there's hardly anything there. That's what makes it a gas, right? There's hardly anything there. There's a huge amounts of free space between them. Okay, they're going to travel forever if they even collide because they're so small in the first place. Well, forever for them. For us, it's the size of a box. But for a gas molecule, that's like miles and miles and miles of empty space. They're not going to see anything. Molecules move in straight lines in all directions and over a range of speeds. Okay, I wish the animation would have hit the range of speeds a little bit better, but I guess we just have to imagine that. Forces of attraction and repulsion between gas molecules is negligible except when they collide. Okay, so forces of attraction. So molecules could actually stick together? Christine, what would happen if two molecules stuck together? Would you have a gas anymore? Or would you start to form what? What would you start to form? If these little gas molecules start sticking together, attraction, start forming a, well, what state? Solid if you make them really slow down, but they're still kind of sloshing around. Probably start forming a liquid. What's the word for that? Starts with a C. Condensation. Can an ideal gas do that? No, they're just theoretical points in space. They can't do that. Okay. So, but they're saying that forces of attraction and repulsion between gas molecules is negligible. It has to be. Otherwise, they're going to start forming a liquid. Okay? So you don't want them to be sticking together. But they do if you make it cold enough, or is it hot enough? Which one would happen, Frankie? If you want condensation to happen and have these gas molecules to start sticking together, because they're moving so slowly, you'd want the temperature to be really hot. They'd be moving faster or slower. Cold, right? Because then they'd be moving so slow, they start sticking together. Okay. When gas molecules do collide, the collisions are elastic. All right. Who's had physics in high school? Okay, there's some people here. Okay, you had two types of collisions. You had elastic and inelastic. I'm sitting there at the stoplight, playing with my new phone, texting or whatever. Light turns green, I should go, but I don't. Jesus is just flying behind me. He expects me to move, but I don't. Bam! Elastic or inelastic collision. His car's all messed up. My back is all messed up. It's inelastic, right? A lot of that energy went into changing the form of the objects that collided, right? Because you can't create or destroy energy. So whatever energy you started out with, you have to end up with that after the collision. So a lot of that energy that Jesus' car was moving, right, deformed our cars. Yeah, we probably moved a little bit afterwards, but inelastic. Sorry, that's inelastic. Elastic. Gilbert, if his car slammed into mine and it was an elastic collision, would our cars deform? Anybody? No. Yeah, it'd be like pretty much like bumper cars, right? The energy goes into, where does the energy go then? Because their bumper cars are moving at the same speed towards each other, right? Or different speeds, whatever. Whatever speeds they're going at, they collide. They're not going back at the same speed. They're all both going back slower, pretty much. Where'd the energy go? Pretty much, yeah. The bumper absorbed some stuff. So it's not quite an elastic collision, a bumper car, right? Because that bumper's moving. But this is what type of collision? Elastic. All right, they're moving, but they pretty much slow down or stop when I get it. Where's the energy going? You can hear some of the energy, but that's not where most of it's going. Where's it going, Kimberly? Same with these molecules. They collide, their collisions are elastic. Where's the energy go? They collide with the wall of the container, and they start slowing down a little bit in comparison to before they collided with the container. Where'd the energy go? You don't know? Well, let's see if we can find out then. It's kind of dangerous, so careful. Can you smell it? I smell smoke. Heat. It goes into heat. So hot that it burns the paper. You can see there's actually brown tinges in there. Right? So it goes into heat. Okay. The average kinetic energy of gas molecules is directly proportional to the temperature of the gas. Okay. Alyssa, I think you nodded your head that you had physics. They pretty much didn't you nod your head?
Yes.
Okay. In that class, they pretty much divvied all energy into two forms. It was kinetic energy and, it starts with a P, potential energy. Okay, kinetic energy is, which one is the energy of stuff moving around? Kinetic energy. Potential energy is just this. You can't be moving, right? But it has potential energy, because if I drop it, it could hurt my foot, right? So it has energy. But kinetic energy is the energy of motion. So you can make the energy of motion of gas molecules that are kinetic energy go higher, well, directly proportional. That means, right, you make one bigger, the other one has to get bigger. So you make temperature bigger, kinetic energy has to get bigger. We already know that. You already told me. I crank up the temperature, things move faster, right? Okay. So as these little animations are going, you just kind of fill in the blanks here, okay?
The ideal gas law relationship between pressure, temperature, volume, and number of atoms can be demonstrated using a piston. As the volume of the cylinder decreases under constant temperature and number of atoms, the pressure increases due to the increased rate of collisions against the wall of the cylinder.
Okay, did you catch all that?
The ideal gas law relationship between pressure, temperature, volume, and number of atoms can be demonstrated using a piston. As the volume of the cylinder decreases under constant temperature and number of atoms, the pressure increases due to the increased rate of collisions against the wall of the cylinder.
Amy, got all those? Okay, so once we get all the answers, then we'll watch the whole thing without having to write stuff down. But okay, here's experiment 2.
We now lock the piston to create a constant volume and number of atoms. Increasing the temperature results in increased kinetic energy for the atoms. The result is an increase in both temperature and pressure. Removing the heat source allows the kinetic energy of the atoms to dissipate to the surroundings, and the system returns to original conditions. Lock the piston to create a constant volume and number of atoms. Increasing the temperature results in increased kinetic energy for the atoms. The result is an increase in both temperature and pressure. Removing the heat source allows the kinetic energy of the atoms to dissipate to the surroundings, and the system returns to original conditions.
Got all those answers? Gilbert, Hazel, which one did you miss? Hazel's will tell you. Which one did you miss? You got it? Okay, experiment 3.
With pressure and temperature held constant, additional atoms can be added to the cylinder. This results in an increased volume in the cylinder. If we double the number of atoms, the volume will double under these conditions. The can be added to the cylinder. This results in an increased volume in the cylinder. If we double the number of atoms, the volume will double under these conditions.
Okay, so let's watch this whole thing without having to write anything down. So just the movement, and I think the animation helps me remember this stuff.
The ideal gas law relationship between pressure, temperature, volume, and number of atoms can be demonstrated using a piston. As the volume of the cylinder decreases under constant temperature and number of atoms, the pressure increases due to the increased rate of collisions against the wall of the cylinder. We now lock the piston to create a constant volume and number of atoms. Increasing the temperature results in increased kinetic energy for the atoms. The result is an increase in both temperature and pressure. Removing the heat source allows the kinetic energy of the atoms to dissipate to the surroundings, and the system returns to original conditions. With pressure and temperature held constant, additional atoms can be added to the cylinder. This results in an increased volume in the cylinder. If we double the number of atoms, the volume will double under these conditions.
Okay. So there's our 3 experiments. So what I'd like to do is work together on, you guys work together on answering these, and if you have any questions, just ask. But there's a couple parts in here where, like right here, it's not very well explained. This Charles's law, they're saying that volume is directly proportional to temperature, right? So that means if you make volume bigger, temperature has to get bigger. But what they don't say is that, hey, you got to keep the pressure constant, right? For this to work. If you want to make the temperature bigger, keep the pressure constant. The volume has to get bigger. For this one, Boyle's law, now they're inversely proportional. So if you make the pressure bigger, volume has to get smaller because they're inversely proportional. But the temperature has to be constant. So otherwise it's not going to work. Okay. So using these ideas that you've seen with kinetic molecular theory of gases, try to answer all these questions. And this is the big one at the end. You want to make sure you get the right answers for this. So talk with the folks around you and try to answer all these. I'll be glad to help you out if you get stuck.